Thankfully, we've seen a few algorithms already, including in that week 0. And now we're going to give it a more formal name. Linear search is what we did with that phone book first off by searching it page by page by page, looking for my phone number in that particular example. And so the difference today is that unlike us humans who can sort of look down at a phone book page and see a whole bunch of names and numbers at once, unlike a human who can look at an array on the board a moment ago and sort of see everything at once, we need to be more methodical, more deliberate today so that we can translate week 0's ideas now, not into even pseudocode, but actual C code. And so wonderfully, here at the American Repertory Theater, as we are on Harvard's campus this semester, we've been collaborating with the whole team here who are much more artistically inclined than certainly I could be on my own here. And we have these 7 wonderful doors that were previously used in various theatrical shows that took place here in this theater. And we've even collaborated with the theater's prop shop, who in back have wonderfully manufactured some delightful numbers and brought them to life, which is to say that behind each of these 7 doors is a number. And this is going to be an opportunity now to really hammer home the point that when we want to search for some number in an array, it's pretty equivalent to having to search for a number, in this case, behind an otherwise closed door. You and I can't just look at all of these doors now and figure out where a number is. We have to be more methodical. We have to start searching these doors, maybe from left to right, maybe from right to left, maybe from the middle on out. But we need to come up with an algorithm and ultimately translate that to code. So for instance, suppose I were to search for the number 0. How could we go about searching methodically these 7 wooden doors for the number 0? Let me take a suggestion from the audience. What approach might you take? What first step would you propose I take here on my own with these doors? Any recommendations? How do I begin to find myself the number 0? Florence, what do you propose?
I would propose starting from the left, since 0 is a smaller number.
OK, good. And hang in there with me for just a moment. Let me go ahead and start on the left as Florence proposes. Go ahead and open the door, and hopefully, voila, no. It's a number 4, so it's not a 0. So Florence, what would you propose I do next?
I would probably start in the middle somewhere, if in case, I don't know, it's going down by 1. So. OK, so maybe it's going down. So let me go ahead and try that. So you propose middle. I could go over here, and voila. Nope. That's the number 2. And I wonder, where else should I look? I'm a little curious. I'm a little nervous that I ignored these doors. So Florence, if you don't mind, let's go ahead and look here. And nope, that's the number 6, it seems. Let's go ahead and check in here. The number 8. So they're kind of going up and down. So Florence, how might I finish searching for this number? What remains to be done, would you say? Probably start from the right.
OK, so I could start from the right now and maybe just go over here. And voila. And there it is. So we found the number 0. So let me ask Florence, what was your algorithm? How did you go about so successfully finding the number 0 for us?
I guess I initially tried starting by going down by 1. So if the number was not at the left, then going to the center, which is halfway in between.
OK.
Then going to the right or there, I don't know.
And playfully, how did that work out for you, going to the middle? Better, worse, no different?
I mean, I guess maybe it helped a little bit to then go all the way to the right.
OK, yeah, we might have gleaned some information. But let's go ahead and take a look at all of the doors for a moment. There's that 4 and the 6 again. Here's that 8 again. Over in the middle, we had the 2 again. Over here, we have a 7 for the first time. Over here, we have a 5. And then, of course, we have a 0. And if you took all of that in, honestly, Florence, you and I, we couldn't really have done any better. Because these numbers, it turns out, are just randomly arranged behind these doors. So it wasn't bad at all that you kind of hopped around. Although the downside is if you hop around, you and I as humans can pretty easily remember where we've been before. But if you think about how we would translate that to code, I feel like we're starting to accumulate a bunch of variables maybe, because you have to keep track of that. So frankly, maybe the simplest solution, maybe the simplest solution would have been where we started in week 0, where we just take a very simple, if naive, approach of starting with our array, this time of size 7, behind which are some numbers. And if you don't know anything about those numbers, honestly, the best you can do is just that same linear search from week 0. And just check one at a time the values behind each of these doors and just hope that eventually you will find it. So this is already sort of taking a lot of time, right? If I do this linear search approach like I did in week 0, I'm potentially going to have to search behind all of those doors. I'm going to have to search behind all of those doors. So let's consider a little more formally exactly how I could at least implement that algorithm. Because I could take the approach that Florence proposed of just kind of jumping around and maybe using a bit of intuition. But again, that's not really an algorithm. We really need to do something more step by step. And in the meantime, let's go ahead, Joe, and let's close the curtain and see if we can't clean those up with another problem in a moment while we consider now linear search and the analysis thereof. So with linear search, I would propose that we could implement it in pseudocode first, if you will, like this. For I from 0 to n minus 1, all right, we'll see where we're going with this. If the number is behind the ith door, return true. Otherwise, at the very end, return false. So it's a relatively simple translation into pseudocode, much like we did with the phone book some time ago. And why, though, these values? Because I'm now starting to express myself a little more like C, even though it's still pseudocode. So for I from 0 to n minus 1. So computer scientists tend to start counting from 0. If there's n doors, or 7 doors in this case, you want to go from 0 on up to 6, or from 0 on up to n minus 1. So this is just a very common way of setting yourself up with a for loop, maybe in C, maybe in pseudocode in this case, that just gets you from left to right, algorithmically, step by step. If a condition, number is behind the ith door, ith just being a colloquial way of saying what is behind the door at location I, go ahead and return true. I have found myself the number I want, for instance, the number 0. And then notice that this return false is not part of an else, because I don't want to abort this algorithm prematurely and abort simply because a number is not behind the current door. I essentially want to wait all the way to the end of the algorithm after I've checked all n doors. And if I have still not found the number I care about, then and only then am I going to return false. So a very common programming mistake might be to nest this internally and think about things in terms of ifs and elses. But you don't need to have an else. This is kind of a catch-all here at the very end. But now let's consider, if this is the pseudocode for linear search, just what is the efficiency of linear search? What is the efficiency of linear search? Which is to say, how well designed is this algorithm? And we gave ourselves a framework a moment ago, big O notation, which is an upper bound, which we can think of for now as meaning like a worst case. In the worst case, how many steps might it take me to find the number 0, or any number for that matter, among n doors? Is it big O of n squared, big O of n times log n, big O of n, big O of log n, or big O of 1, which again just means a constant fixed number of steps? Brian, could we go ahead and pull up this question? Let me go ahead and pull it up on my screen as well. If you go to our usual URL to propose what you think an upper bound is on the running time of linear search. OK, indeed. If we consider now the running time of linear search, it's going to be big O of n. Why is that? So in the worst case, the number I'm looking for, 0, might very well be at the end of that list, which is going to be on the order of n steps, or in this case, precisely n steps. So that's one way to think about this. Well, now let me ask a follow-up question, proposing instead that we consider omega notation, which is a lower bound on the running time of an algorithm. Brian, could we go ahead and ask this question next? At that same URL, we'll see a question asking now for the possible answers for the running time, for a lower bound on the running time of linear search. So let's go ahead and take a look at this one here. And in just a moment, we'll see as the responses come in, about 75+% of you are proposing that it's actually omega of 1. So omega is a lower bound. 1 refers to constant time. And why is that? Let me just take a quick answer on this point. Among the 75% of you who said 1 step, or a constant number of steps, why is that? How do you think about this lower bound on running time? How about from Keith? Why omega of 1?
Yeah, you can just open it and be lucky and find it in the first door.
Yeah, so it really speaks to just that. You might just get lucky, and the number you're looking for might be at the very first door. So the lower bound, in the best case, if you will, of this algorithm, linear search, might very well be omega of 1 for exactly that reason, that you have to get lucky, and the element might be there at the beginning. So that's pretty good. We really can't do any better than that. So we have this range now of a lower bound from omega of 1 on up to big O of n being an upper bound on the running time of linear search. But of course, we have this other algorithm in our toolkit. And recall from week 0 that we looked at binary search, although not necessarily by name. It was that divide and conquer third algorithm where we took the phone book and split it in half and half and half again. Now, while I fumbled there, Joe kindly has given us a new set of doors. If Joe, we could go ahead and reveal our 7 doors again, behind which we still have some numbers. But I think this time I'm going to be a little better off. Cue Joe and the doors behind. There we go. So we have our same 7 doors, but behind those doors now is a different arrangement of numbers. And suppose this time I want to find myself the number 6. So the number 6 will change the problem slightly, but I'm going to give you one other ingredient this time, which is going to be key to this working. Why were Florence and I able to do no better than linear search before? Why were Florence and I able to do no better than randomly searching even last time? What was it about the array of numbers or the array of doors that did not allow me previously to use binary search? Iris, what do you think?
It's because we didn't know if the numbers were sorted or not.
Yeah, we didn't know if the numbers were sorted or not. And indeed, barring that detail, Florence and I really couldn't have done any better than, say, linear search. So this time, though, Joe has kindly sorted some numbers behind these doors for us. And so if I want to search for the number 6, now I can begin to use a bit of that information. So you know what? I'm going to start just like we did with the phone book and start roughly in the middle. And voila, number 5. All right, so we're pretty close. We're pretty close. But the thing about binary search, recall, is that this is now useful information. If the numbers are sorted behind these doors, all of the doors to the left should presumably be lower than 5. And all of the doors to the right should presumably be larger than 5. Now, I might kind of cut a corner here and be like, well, if this is 5, 6 is probably right next door, literally. But again, algorithmically, how might we do this? We don't want to necessarily consider these special cases. So more generally, it looks like I now have an array of size 3. So let me go ahead and apply that same algorithm, voila, to the middle. Now I have the number 7. And now it's becoming pretty clear that if the number 6 is present, it's probably behind this door. And indeed, if I now look at my remaining array of size 1, and voila, in the middle, there's that number 6. So this time, I only had to open up 3 doors instead of all 7 potentially, or maybe all 6 doors to find my way to that number because I was given this additional ingredient of all of those numbers being sorted. So it would seem then that you can apply the better, more efficient, better designed algorithm, now known as binary search, if only someone like Joe would sort the numbers for you in advance.